Hi, today we're going to go over domain and range, two important concepts in Algebra 1 that show up in a whole bunch of different ways on a whole bunch of different types of assignments and problems. We're going to go over some tips and strategies to make these problems a little bit easier. So first, it's good to clarify what exactly domain and range are. And at the most fundamental level, domain and range refer to the inputs and outputs of a function, with domains being the inputs and range being the outputs. And that doesn't make sense. Let's try to clarify. So in an earlier video, I discussed that functions were a lot like assembly lines, right? Where you have one product coming in, it gets transformed, something happens to it inside the function, and then it comes out with a certain operation being performed on it, right? And if you remember, for a function, to be a function, for every single input, there has to be exactly one output. There can't be more than one output for a single input, right? We can't have a box that's stamped in the stamping machine, but it comes out stamped and with a bow on top, right? That's not how it works. So, what are domain and range, and how can we execute them appropriately? Well, we can use two main strategies. The first is thinking of functions instead of like a graph or line as a series of points, right? Because when you think about domain and range as a series of points, they're a lot easier to deal with, right? If I gave you, let's say I have a function f, which is just, it's discrete, so it's the points 2, 3, and 4, 5. And I asked you to list the domain and range of this function. That's pretty easy. The domain is the inputs, right? And we know when we're graphing, the x's are our inputs, and the y's are our outputs. So my inputs, my range, the inputs, my domain, are just 2 and 4. And my range is just 3 and 5. Well, that's really easy. It's just the domain is the x and the range is the y. Now, where it gets complicated is when you have continuous functions, which is why I recommend thinking of continuous functions at their most basic points, right? Because imagine I have something like this: y equals x. We don't have a nice, or I guess I should say f of x equals x, right? We have something like this, right? But we don't have a clearly defined range of points that we can go out and find the domain and the range, the inputs and the outputs. But we can make this process a lot easier if we think about this function as just a collection of points, just a whole bunch of points, right? We have a whole bunch of negative points, actually all the way down to negative infinity, right? So we can say, hey, if negative infinity is a value, we'll have negative infinity, negative infinity. Since we have, if you plug in x, we just get x as f of x, right? On the other hand, we'll have negative infinity plus 1, negative infinity, all the way up to 0. Then we'll go 1, 2, 3, 4, 5, all the way up to infinity. And infinity, right? Because you can plug in an x, we get the same value, right? So we have every point from negative infinity to infinity, right? And that becomes a lot easier to work with, right? We can very clearly see, okay, here are our inputs, and here are our outputs. We know that this function, because it's continuous, has every single value between those values. We can say, our domains, everything from negative infinity to positive infinity. And there are a couple ways to write this. You could say infinity is greater than x, which is less than infinity. Or you could say, using interval notation, which is the same thing, negative infinity to infinity. An interval notation is a kind of compressed way of expressing that, hey, this function has all the values of x as inputs between negative infinity and positive infinity. We'll just write that. We can use that as parentheses to symbolize these signs. All right. We can do the same thing with range. We know that this function has every y value from negative infinity to infinity. And of course, we can also write that as negative infinity, infinity. Notice in each of these I included the x and the y, because remember, domain refers to x values and range refers to y values, right? If I said, here, x, well then this wouldn't be the range, right? Because x refers almost exclusively to my inputs, right? In my function, right? I'm plugging in x in my function. It is my input. It's not my output. My output is f of x. Or y, you could say. But that covers the basics of domain and range. But let's say we have something a little more crazy, right? Let's say I have an exponential function. Exponential functions are interesting. And let's say, it's f of x equals 2 to the x, right? Let's say that's our exponential function. If we were to graph this, we get something like this, right? Starts out small and goes all the way up to infinity. And now, let's say we were asked to find the domain and the range. Once again, let's think about this as a series of points, right? We start at 1 and we go 2, 3, 4. We're always increasing, always increasing, all the way up to infinity, right? So we have infinity and then 2 to the infinity, if you will, which is still infinity. What about on the other hand? Let's say we're getting smaller and smaller and smaller. Now, what's interesting is we notice this gets smaller and smaller and smaller, but it never actually gets to 0. We can confirm this by just saying 0 equals 2 to the x, right? What power can I raise 2 to get 0? Well, if I do 2 to the 0, I'll get 1, because anything raised to the 0 power is 1. But on the other hand, if I would do like a negative exponent, like 2 to the negative 1, that's just 1/2. 2 to the negative 2, that's 1/4. And I can keep making my exponents more and more negative. I can do 2 to the negative 1,000, and I will still get 1 over 2 to the 1,000. So I'll get my numbers smaller and smaller and smaller, but I can never get them to 0. So we can never have the point, negative something, negative infinity 0. We're always going to be close to 0, but not quite at 0. So I can say this, just for my shorthand, we can have negative infinity, not, like this, not 0, right? We can have negative infinity, and we will get really, really close to 0, but we will not have 0. So, how can we write this? How can we write this? So if we were thinking about our domain and range in terms that we normally being taught, the domain isn't really affected by this, right? It still can go to negative infinity. It still can go to positive infinity. It can go for all values between negative infinity and positive infinity. We can write this as this, or since we're just between negative infinity or positive infinity, write it as R, which basically means all real numbers, or every single number, every single decimal between negative infinity and positive infinity, which this graph covers. The range is where things get a little more tricky. Because remember, we don't actually get to 0. We don't. But thankfully, that's actually not as much of a problem. We know we go all the way up to infinity, right? Because here our max point is, infinity, infinity. But we don't get to 0. So we can say, okay, our y's never get to 0, but they do, get close to infinity. We don't do an equal sign here because no value can really equal infinity. Infinity is infinity. It's not like a it's just so big that we're only ever approaching it. We can never reach it and be at infinity. So I correct this as 0, infinity as well. And you'll come across a lot of problems like these, where you'll get values, numbers, or graphs that aren't just infinity, infinity. But if you think about them as a series of points, and then go further and say, okay, well, what points cannot be on this graph? In this case, we couldn't have like negative infinity, 0 on this graph. Then figuring out your domain and range becomes much, much easier. Anyway, that's all I have, and I hope you have a great day and you do great things.